Welcome to today's episode, where we're diving into the fascinating and intricate world of database management. We'll focus on the vital aspects of managing database page caches and the essential role that page replacement algorithms play in optimizing system performance. Along the way, we'll tackle the challenges that arise from subtree operations, the significance of buffering changes, and the mechanisms that help ensure data integrity and durability. So, let's unpack these critical concepts that form the backbone of modern database systems. At the core of database performance is the management of page caches. Now, you might be wondering, what exactly is a page cache? Well, think of it as a memory area that stores data pages that are frequently accessed. This helps reduce the need for disk reads and writes, making everything run more smoothly. However, effectively managing these caches can get complicated, especially when operations on subtrees lead to conflicting structural changes. These conflicts can create real challenges in maintaining both data consistency and overall performance. To navigate these challenges, database systems rely on page replacement algorithms. These algorithms help decide which pages to evict from the cache when new pages need to be loaded. You might have heard of some common strategies like first in, first out, or FIFO, and least recently used, or LRU. FIFO is pretty straightforward. It simply replaces the oldest page in the cache first. On the other hand, LRU keeps track of page usage over time, opting to evict the pages that haven't been accessed for the longest period. But that's not all. We also touched on more advanced algorithms like TinyLFU, or Tiny Least Frequently Used. This approach prioritizes pages based on how often they're used, rather than just how recently they were accessed. By doing this, TinyLFU offers a more nuanced way to manage cache, which can lead to better performance by keeping frequently accessed data in memory longer. This, in turn, reduces the need for those costly disk I/O operations. As we explored the complexities of database operations, we highlighted the importance of buffering structural changes in memory. When modifications are made to data structures, especially in tree-based databases, unbuffered changes can lead to a flood of disk writes if not managed properly. Buffering allows the system to group multiple changes together, which minimizes the number of write operations and enhances overall performance. By holding changes in memory temporarily, databases can optimize when and how data is written to disk. This not only speeds things up, but also reduces wear on storage devices, which is particularly crucial in high transaction environments. So striking the right balance between memory usage and disk writes is key to maintaining efficient database operations. Now let's talk about a crucial component in ensuring data integrity and durability, the write-ahead log, or WAL. The WAL acts as a safeguard against data loss by keeping an immutable, append-only log of all transactions. This log captures every write operation before it's applied to the database, ensuring that if there's a system failure, the database can be restored to a consistent state. Each entry in the WAL gets a unique log sequence number, or LSN, which is vital for maintaining the order of operations. This sequential logging helps the database confirm transaction completions and recover from failures effectively. However, it's important to keep in mind that I/O errors can complicate this whole process. If these errors occur during write operations and aren't reported properly, it can lead to a false sense of security regarding data safety. As we delve deeper into the implications of I/O errors, we discussed how they can impact data integrity. When errors go unreported, they create vulnerabilities in the recovery process. For example, if a checkpointer misses error notifications because of a limited number of open file descriptors, it might fail to capture critical information needed to maintain data consistency. To mitigate these risks, it's crucial to consider potential failure scenarios when designing recovery mechanisms. The WAL plays a vital role here, providing a reliable framework for tracking changes and ensuring that all transactions can be accounted for, even in the face of unexpected errors. We also examined the potential pitfalls of synchronization processes, particularly in PostgreSQL. Improper handling of dirty pages, those that have been modified in memory but haven't yet been written to disk, can lead to data loss or corruption. It's essential to manage these pages correctly to maintain the integrity of the database. Synchronization mechanisms need to be carefully designed to prevent conflicts and ensure that data remains consistent across multiple transactions. Understanding how to handle dirty pages effectively is crucial for database administrators and developers, as it directly impacts the reliability of the system. To wrap up today's episode, we've highlighted the complexities of managing database page caches, the critical role of page replacement algorithms, and the importance of data integrity mechanisms like the write-ahead log. We've explored how buffering changes can minimize disk writes and discussed the risks associated with I/O errors and synchronization processes. As we navigate the ever-evolving landscape of database management, grasping these concepts is vital for ensuring the reliability and efficiency of modern database systems. Thank you for joining us today, and we can't wait to explore more topics in our next episode.